All right, let's talk about the invisible engines that run pretty much our entire digital lives. Databases. Every single time you check your bank account or you're scrolling through social media, they're the ones working tirelessly behind the scenes, just quietly making sense of this absolute universe of information.
I mean, really think about that. How can one platform show you a photo your friend just posted, recommend a new song that you might actually like, and process a payment all at the exact same time for millions and millions of people? Well, the secret isn't some single magic box. Nope. It's a whole ecosystem of different kinds of databases, and each one is like a specialized tool for a very specific job.
So, before we dive into all the different flavors of databases out there, let's just start with a solid foundation. What even is a database? At its heart, it's a concept you're probably already familiar with. The key word there, the most important word, is organized. A random folder full of documents on your computer? That's not a database. A database imposes structure, it imposes order. It's a system run by special software. We call it a DBMS, a database management system, that lets us define, create, find, and manage all that data super efficiently.
Yeah, the index card analogy is just perfect. Imagine a gigantic library filled with these cards. The database is the library, and the DBMS, that's the lightning fast librarian who can find, update, or file any card you ask for in just a fraction of a second.
Okay, so for our tour, let's start by hopping in a time machine and heading back to the 1970s. Back then, the world ran on really structured, predictable information. Things like employee records, inventory lists, financial ledgers. The big challenge was figuring out how to digitize this orderly world without, losing all that precious structure. In the early days, just getting a piece of data was complicated. Programmers literally had to navigate this complex web of pointers and links, almost like following a treasure map through a maze. But then, in 1970, a researcher at IBM named Edgar F. Codd published this revolutionary paper. Now, it took about another decade for computers to get powerful enough to actually use his idea, but when they did, it completely changed the game. This, right here, was a massive shift in thinking. Codd's big idea was that we should stop telling the database how to find data step by step. Instead, you could just declare what data you wanted, and the system itself would figure out the smartest, most efficient way to go get it for you. It was just a huge leap forward in both simplicity and power. And this is Codd's model in action. It's beautiful, right? Data is organized into these neat tables with very strict rows and columns. Each row is a unique record, and it's identified by a primary key. In this case, it's the user ID. That key makes sure there are no duplicates, and it acts as the unique ID we use to link or relate this table to other tables. So, where is all this strictness actually a good thing? Well, think about your bank. When you transfer money, that transaction has to be perfect, right? It can't be half done. Relational databases guarantee this with something called ACID properties. It's basically a rock-solid promise that every transaction is processed completely and reliably, or not at all. This makes them the absolute bedrock of finance and commerce. But then the internet happened, and suddenly data wasn't just in neat, predictable tables anymore. Oh no, it was messy, it was unstructured, and it was growing at this absolutely explosive rate. We're talking social media posts, user profiles with all sorts of different fields, massive log files. The rigid relational model, it started to show its limits. And this chaos led to the rise of NoSQL. Now, the name's a little misleading. It really just means not only SQL. It's a totally different philosophy. Instead of a fixed structure or schema that you have to define up front, you get flexibility. And instead of scaling up by buying one massive, super expensive server, that's vertical scaling, you scale out by just adding more and more cheaper servers to a network. That's horizontal scaling. The real beauty of NoSQL is that it isn't just one single thing. It's a whole family of different database types, and each one is designed like a specialized tool for a particular kind of data problem. Okay, let's look at the big three. First, you've got key value stores. They're the simplest. They work just like a dictionary. You give it a key, it gives you the value. They're incredibly fast for looking things up, which is perfect for temporary data, like, say, the items in your online shopping cart. Second, document databases. They store info in these flexible documents. A social media profile is a great example, right? One user might list their hometown, another might not, and the database handles that kind of flexibility perfectly. And finally, graph databases. These are built for connections. They model data as nodes, like people, and the relationships or edges between them. This makes them amazing for mapping out social networks. But of course, technology never ever stops evolving. Today, the demands of artificial intelligence and this growing need for cryptographically secure data are pushing the boundaries all over again, and that's leading to a whole new wave of specialized databases.
Just pause and think about this for a second. A traditional database can find an exact match for a file, no problem. But how does an AI find all the pictures that have the concept of a dog catching a frisbee, even if the pixels are totally different in every single photo? It needs to understand meaning.
This, my friends, is the job of a vector database. It takes data, an image, a chunk of text, whatever, and it converts it into a mathematical representation called a vector. So instead of searching for exact matches, it searches for other vectors that are close by. And in this world, closeness equals similarity in meaning. It's pretty cool. This tech is behind some of the most exciting AI features we see today. It's what powers that search by meaning in your photo apps and those really sophisticated recommendation systems. It's also a key part of what we call retrieval augmented generation, or RAG. That's a fancy way of saying it's how we give AI models access to specific, private knowledge so they can answer questions accurately about it. Now, at the same time all this AI stuff is happening, a different kind of database is tackling another huge modern problem: trust. An immutable database works like a secure digital ledger. You can only add new data. You can never, ever alter or remove what's already there. Each new entry is cryptographically chained to the one before it, creating this perfectly tamper-proof audit trail. So, as we've seen, the database world has just exploded from this one-size-fits-all model into this rich, diverse toolbox. And the central theme, the main takeaway for modern data, is that there is no single best database anymore. So here's a quick cheat sheet to pull it all together. If you need absolute data integrity, like for bank transactions, you use Relational. For the kind of flexibility you need for social media profiles, you'd choose a document database. To map out all the connections in a social network, Graph is king. For any kind of AI-powered similarity search, it's got to be a vector database. And for a verifiable tamper-proof record you can trust, you need an immutable database. It's all about the right tool for the right job. So we've gone from simple digital filing cabinets to being the engines of artificial intelligence and digital trust. Databases have just constantly evolved to meet our world's ever-changing demands. And that leaves us with a pretty fascinating question to think about. As our data becomes even smarter and more interconnected, what new challenges are coming our way? And what will the next generation of databases be built to solve?